Good day, everyone. In our previous lecture, we mentioned that convolution codes are codes in which each output block depends not only on the current or present input block, but also on some of its past inputs as well. And in this series, we are going to be investigating the possible ways of implementing the convolution coder. And some of the notable techniques are the polynomial matrix method, the scalar matrix method, the shift register method, then we have the state diagram method, and also we have the tree diagram method, and also the Trellis diagram method. So we'll be investigating all of these in this lecture. And so let us begin with the polynomial matrix method. So if we are given a field, say f sub z, for which z is a prime number, okay, and that the input alphabets are identified with a finite field, say they are elements of a finite field, say f sub 2, then an NK convolution code may be characterized by our K by N generator matrix, which is G, such that the entries G sub ij are polynomials over the field f sub 2. Now, if we are given, for instance, say a 2x1 convolution code, such that the generator polynomial is the same as x squared plus 1, x squared plus x plus 1. And then we are also given a 3x2 convolution code, such that the generator matrix is given by 1, 0, 0, 1, x plus 1, x. Then the memory of the encoder, say m, is defined as the maximum value of the degree of the polynomial, that is given over the dimensions j and the degree g, j, such that in this case, for the 2x1 convolution code, now you observe that the maximum degree of the polynomial x here, x squared plus 1 is 2, and that of x squared plus x plus 1, the maximum degree here is 2, so the memory is 2. And for the 3x2 coder or convolution code, then the memory here, since the power of x is 1, is equal to 1. Also, we define the constraint k, which is the same as n plus 1, and it is the size of the shift register in the memory encoder without feedback. So it implies that the number of stages needed for the combinational logic to produce the output bits here will be n plus 1. And in this case, the constraint k is 2 plus 1, which is equal to 3. And in this case, the constraint is 1 plus 1, which is equal to 2. And then we also define the rate. The rate of the code is the ratio of the message bit to the block length. Now, in this case, the message bit is k, which is equal to 1, and the block length n is equal to 2. So for this, the rate is the same as 1 over 2. So this is a half rate convolution encoder. And in this case too, n is 3 and k is 2, such that the rate is the same as 2 over 3. So this is 2 over 3 rate encoder, convolution encoder. Now, to use the generator matrix G to encode scalar information, we want to use it to encode scalar information. The information bits must be mapped into the coefficients of the k-tuple polynomial, say I being the same as I naught of x, I sub 1 of x, all the way to I sub k minus 1 of x. And then the code word C, which is an n-tuple of polynomial given as C naught of x, C sub 1 of x, all the way to C sub n minus 1 of x, therefore gives us the product of the information polynomial and the generator polynomial, where the dot here is the vector matrix multiplication. And note that the generator matrix is the row space in G. So if we are given the information polynomial, for instance, information polynomial, say I being the same as x cubed plus x plus 1, and then we are given the generator polynomial, so G being the same as x squared plus 1, comma, x squared plus x plus 1, then the polynomial code word C would be the multiplication of the information polynomial and the generator polynomial, which is the same as x cubed plus x plus 1 times x squared plus 1, comma, x squared plus x plus 1. Now, when we expand this, C will be the same as x cubed plus x plus 1 times x squared plus 1, comma, x cubed plus x plus 1 times x squared plus x plus 1. And this will be the same as x to the power 5 plus x cubed plus x cubed plus x, then plus x squared plus 1, comma. So we have x to the power 5 plus x to the power 4 plus x cubed times this now plus x squared plus x squared plus x plus 1. Now by modulo 2 addition, then x cubed plus x cubed will be equal to 0. So this will truncate this, right? And this will also truncate this. The same goes for x squared plus x squared is equal to 0, and x plus x is equal to 0. More like 1 plus 1 modulo 2 is 0, and 0 plus 0 is also 0. So all of this truncate themselves. So polynomial code word is the same as x to the power 5 plus x squared plus x plus 1, comma, is now x to the power 4, no, to the power 5 rather, to the power 5 plus x to the power 4, then plus 1. Perfect. So if we also consider for the 3x2 convolution code, such that the information polynomial is given by x squared plus x, comma, x cubed plus 1, such that the generator matrix is given as 1, 0, 0, 1, x plus 1, and x. Then the polynomial code word, same as the information polynomial times the generator polynomial, which is the same as x squared plus x, comma, x cubed plus 1 times 1, 0, 0, 1, x plus 1, x. So when we open this up, then C is the same as x squared plus x times 1, x squared plus x, all times 1, then x cubed plus 1, all times 0, then x squared plus x, all times 0, then x cubed plus 1, all times 1, as a row times each column, then x squared plus x times x plus 1, then x cubed plus 1 times x. Now, this we truncate this because they are multiplied by 0. Then we have x squared plus x, 0, and 0 x cubed plus 1. Then here we have x cubed plus x squared plus x squared plus x. Then here we have x to the power 4 plus x. Now, by modulo 2 addition, this will truncate this. So we have c equal to x squared plus x, 0, have 0, x cubed plus 1. And here we have x cubed plus x. And here we have x to the power 4 plus x. Now, the code word is a row space of C, row space of C, such that this is now equal to x squared plus x plus 0, x squared plus x plus 0, comma, 0 plus x cubed plus 1, comma, x cubed plus x to the power 4 plus x. Once again, by modulo 2 addition, we get rid of this. So C will be the same as x squared plus x, comma, x cubed plus 1, comma, x to the power 4 plus x cubed. That is the polynomial code word. Now let us consider the scalar matrix method. Now, if we assume a polynomial code word, C in the same as C naught of x, C1 of x, all the way to Cn minus 1 of x, obtained by interleaving the polynomial coefficients. And if the jth polynomial is C sub j of x being the same as Cj naught plus Cj1 of x, which is J1x, plus all the way. Then the scalar representation C may be given as C equal to C00, C sub 1, 0, C sub 2, 0, all the way to C sub n minus 1, 0. Then we have C sub 0, 1, then we have all the way to C sub n minus 1, f, all the way. So let's assume this is some equation star. Now, since the generator matrix of the convolution code with generator matrix G is the row space of G, then the scalar version of G with the property that the scalar code word is defined by the equation star given here, forms the row space of G of the scalar G. Now, if we assume that the expansion of G as a polynomial of degree n with coefficients G sub p such that they are k by n scalar matrices, will be given by G in the same as the summation for p equal to 0 to n G sub p x to the power of p. Now, if we are given the generator matrix, say G equal to x squared plus 1, x squared plus x plus 1, then the scalar generator matrix G will be given as sum of, as p taking values from x to n, 0 to n, so p will be equal to G naught S naught plus G1 S1, plus it's a sum, okay, x to the power G2 S to the power of 2 plus all the way to Gn S to the power of n. So this will be the same as G naught because x to the power of 0 is 1 plus G1 x plus G2 x squared all the way to Gn S to the power of n. So now that G is given by this as s squared plus 1, s squared plus x plus 1, so we can rewrite G in this form such that we have 1 here for rearrange is times x to the power of 0 plus now x have no parameter here, so it is 0 dot x to the power of 1 plus 1 times x squared. So it's another way of rewriting this, comma. So in this case, yes, 1 dot s naught plus 1 dot x plus 1 dot x squared. So in this case, we can rewrite this to say 1, 1, that is 1, 1, x naught plus 0, comma 1, 0, comma 1, x plus 1, comma 1, 1, comma 1, x squared, such that when we take the scalars of this, then the scalar generator matrix would be the same as 1, 1, 0, 1, 1, 1. Now, if we are given some, say, convolution code here, being the 2 by 1 convolution code as given initially, then we may be able to extend this into the generator matrix of some arbitrary values. Okay, but you'll observe that n is the same as 2, which is the block length, such that this scalar, or better still, the scalar polynomial values will have to be shifted by the block length, such that the generator matrix, given that G is the same as 1, 1, 0, 1, 1, 1, will now become 1, 1, 0, 1, 1, 1. Since it is a 2 by 1 convolution code, now n is equal to 2, which is the block length. So it means that this sequence will be shifted by 2-bit space, which is the length. So we now have it repeated here, 1, 1, 0, 1, 1, 1. And the same happens again. We shift by 2 bits, which is the block length. So we have 1, 1, 0, 1, 1, 1. And we can go on and on. So 1, 0, 1, 1, 1. And so we realize that this goes into some infinite. So you know that the scalar generator matrix has an infinite number of rows, okay? And infinite numbers of rows and infinite numbers of columns, which implies that the information and code word polynomial may be of arbitrarily large space. But in practice, there will be maximum allowable degree. So hence, the generator matrix will have to be truncated. Will have to be truncated at an allowable degree. Okay? Degree or limit. So, now if the required degree, let's assume the required degree is a degree I sub I of x is less than or equal to L minus 1, for instance, for I taking on values from 0, 1, 2, all the way to k minus 1. And then the code word C is the same as C naught of x, C1 of x, all the way to Cn minus 1 of x, such that each component has degree less than or equal to n plus 1 minus 1, n plus L minus 1. That's n plus L minus 1. Now, the information code word, say I, being the same as I naught x I1 of x all the way to ik minus 1 of x may be represented by KL bits, while the code word may be represented by n into bracket n plus l bits. So therefore, the L truncation of an NK cyclic, convolution code may be viewed as an n into bracket n plus l, comma, KL code. Okay, where this is a linear block code. Hence, the convolution code, the NK convolution code that has been truncated to the n plus l, comma, KL block, linear block code is seen as a special kind of block code. And from this, recall that the rate of the code is the same as the message bit over the block length. So in this case, for the truncated code, the rate of the truncated code will be the same as KL over n into bracket n plus l. Now, which is the same as saying k over n into bracket l over n plus l, and is the same as saying r into bracket l over n plus l. Good. And we can rewrite this by saying L is the same as R into bracket M plus L, right, minus M divided by M plus L, because M minus N is the same as L, right? And therefore, this will be the same as R into bracket M plus L over M plus L minus N divided by N plus L. So this will reduce to 1. So the rate of the truncated code is now seen to be the same as R into bracket 1 minus M over N plus L. And we'll observe that when L is far, far greater than M, okay, then this property here will reduce to 0, such that RL will now be equivalent to R, such that the rate of the truncated code will be equivalent to the rate of the convolution code, which is usually desirable in most practical cases. So let us consider an example. When L is the same as 5, and then the generator polynomial is given as x squared plus 1, comma, x squared plus x plus 1 for the 2x1 convolution code. So let us determine the truncation of this code. So we want to determine the truncation of the 2x1 convolution code. So we have n into bracket n plus l, comma, kl, linear block code, okay, resulting from the truncation, right? For the memory, n is the maximum of the degree, right? For ij. And here it is 2, right? The maximum of the power is 2, so n is equal to 2. So we also have that for the 2, 1 cyclic code, so n, we have n is equal to 2. We have n also to be equal to 2, this nk code, 2, and k is equal to 1. We already know L to be given as 5. Then we can now posit the things properly. So the n into bracket m plus L, comma KL truncated code. We now the n is 2 into bracket m, which is 2 plus 5, comma k, which is 1 times 5. All right. So this will give us 2 into bracket 7, comma 5. So this is going to give us a 14 by 5 truncated code. Recall that G from this, the scalar was 1, 1, 0, 1, 1, 1, which extended infinitely on the matrix. So, in other words, we have 14 columns and 5 rows. So let's place 5 rows of this. So let's see if we're going to get 14 columns. So G5 here, which is the same as the GL, which is a truncation of this code. We have 1, 1, 0, 1, 1, 0, 1, 1, 1. And recall the block length is n. And so this code is going to be, the sequence is going to be shifted by the block length. So we're going to shift by 2. So from here, 1, 1, 0, 1, 1, 1. That's second row. I'm going 5 rows. Then we shift again by 2. 1, 1, 0, 1, 1, 1. Then we shift again by 2. 1, 1, 0, 1, 1, 1. That's the fourth row. And then the fifth row. Shift by 2. 1, 1, 0, 1, 1, 1. So here we go. So we have row 1, we have row 1, row 2, row 3, row 4, and row 5. Perfect. So do we have 14 columns? So let us check. Column 1, column 2, column 3, column 4, column 5, column 6, column 7, column 8, column 9, column 10, column 11, column 12, column 13, then column 14. Perfect. So we have the truncated NK code. Now let's assume we are given information polynomial. Say I being the same as x cubed plus x plus 1. And then the generator polynomial. So G in the same as x squared plus 1, x squared plus x plus 1. Then what is the scalar information? Scalar information. And what is the, from here, And here we can get the scalar code word. Now we know that the polynomial information is given as s cubed plus x plus 1. Now we also know that the scalar information I can be given as the summation for p equal to 0 to n, given I sub p, x sub p, to the power of p. So this will be I naught, x naught plus I1, x1 plus, we have third degree, right? Cube. Now I1, I2, x squared plus I3, x cubed. Okay, so this is going to give us I naught plus I1, x plus I2, x squared plus I3, x cubed. So if we rearrange this, so we are going to get 1 dot x naught plus 1 dot x plus 0 dot x squared, because we don't have x squared here, plus 1 dot x cubed. So this now will be the same as 1 x naught plus 1 x plus 0 x squared plus 1 x cubed, such that the scalar information I will now be equal to 1, 1, 0, 1. Okay? 1, 1, 0, 1. But the polynomial code word C is given as I times G, and this is the same as x cubed plus x plus 1 into bracket x squared plus 1, comma, x squared plus x plus 1, right? This times this. So just like we did in the previous example, that's x to the power 5 plus x cubed plus x squared plus x cubed plus x plus 1. So we have x to the power 5 plus x to the power 4 plus x cubed plus x cubed plus x squared plus x squared plus x plus 1. So by modulo 2 addition, x cubed will truncate x cubed, x cubed will truncate x cubed, x squared will truncate x squared, x will truncate x, so that we have x to the power 5 plus x squared plus x plus 1, comma, x to the power 5 plus x to the power 4 plus 1. Now, recall that the scalar is given as p equal to 0 to m cp x to the power of p, which is the same as c naught x naught plus c1 x1 plus c2 s2 all the way to the power is 5 here, c5 x to the power 5. And then can now rewrite this to say, well, this is the same as, say, 1 dot x naught plus 1 dot x plus 1 dot x squared plus 0 dot x cubed plus 0 dot x cubed, x to the power 4 rather, plus 1 dot x to the power 5, comma, 1 dot x naught plus 0 dot x plus 0 dot x squared plus 0 dot x cubed plus 1 dot x to the power 4 plus 1 dot x to the power 5. So when we collect the like terms, so this will now be the same as 1, comma 1 x naught plus 1, comma 0, comma 0 x plus 1, comma 0 x squared plus 0, 0, 0, 0, x cubed plus 0, 1, x to the power 4 plus 1, 1, x to the power 5, such that the scalar code word will be the same as 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1. Now, if we are given the generator matrix G to be the same as 1, 0, 0, 1, x plus 1, x, this is for a 3 by 2 convolution code, then G is the same as P equal to 0 of n, G sub P, S of P. Now, since P is equal to 1, that's from the generator matrix G, so that's power here is 1. So what we have now is that G is the same as G naught, X naught for all of this, plus G to the power of 1, X1 for this one. Okay? And we can equally rearrange the generator matrix G to be the same as we have 1, 0, 1, 0, 0, 1, 0, 1, then we can bring this out. This is 1, then we have X here, then we have X here. Okay? Now, if we fill this up, so G be the same as 1, 0, 1, 0, 1, 0. Technically, we can fill all of this up with some x to the power of 0 factor. So that would be 0, 0, x, right? And this will be 0, 0, x. So this will be equivalent to this, right? Okay. Now, if that's that, then it means it's another way of saying 1, 0, 1, 0, 1, 0 plus, that's x to the power of 0 plus 0, 0, 1, 0, 0, 1, x to the power of 1, okay, which is equivalent to this. Hence, we have G to be the same as 1, 0, 1, 0, 0, 1, 0, 0, 1, and 0, 1, 0, 0, 0, 1, 0, 0, 1. So, if G is 1, 0, 1, 0, 0, 1, and 0, 1, 0, 0, 0, 1, recall that we have a 3 by 2 convolution code, and observe that n is equal to 3, right? It's nk. So it means that this bit sequence will have to shift by the block length, such that the scalar generator matrix will become the scalar generator matrix will become G, which will extend to some infinite value, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. And since this we all shift by the block length 3, so that's 1, 2, 3. So we start coming from 1, repeat this again, 0, 1, 0, 0, 1, and 0, 1, 0, 0, 0, 1. And then we shift by the block length. So we start here again, 1 0 1 0 0 1 0 1 0 0 0 1, and this will extend to infinity. So once again, the scalar generator matrix has an infinite number of rows and columns, which implies that the information and code word polynomials will be of an arbitrarily large degree. Hence, the need to further truncate this generator matrix. So we need to truncate this generator matrix for applicability, for ease of application. Okay. Now, let us assume once again that we have L to be equal to 3, and then we have the generator matrix 1 0 0 1 x plus 1 x for a 3 by 2 convolution code. So we want to provide the truncation. Okay. Now, for us to be able to do this, then it means that we are looking at the code n into bracket m plus l, comma kl code, right? We already know that L is equal to 3, then N also is equal to 3, K is equal to 2, then M is the power of the polynomial, which is 1, in this case s to the power of 1, x to the power of 1. That's the maximum degree of the power. And now we can now derive our N into bracket M plus L, comma KL code. So this N is 3 into bracket 1 plus 3, comma K, which is 2 times 3. So this is going to give us 3 into bracket 4, 6. So this is going to give us a 12 by 6 linear block code. And for us to get this true, so G sub L, which is equal to G to the power sub 3, now give us some finite. So we have 3. So we have 6 rows, 12 columns. So let us check that out again. We have 1, 0, 1, 0, 0, 1, and then we have 0, 1, 0, 0, 0, 1. Remember? And now n is 3, so we'll have to shift by the block length 1, 2, 3 bit space. Then we have 1, 0, 1, 0, 0, 1, and 0, 1, 0, 0, 0, 1. And once again, we shift by the block length, which is 3. Then we'll repeat the code 0, 1, 0, 1, 0, 0, 1, and 0, 1, 0, 0, 0, 1. So I think we're there. Okay, so we have this. So now we have row 1, row 2, row 3, 4, 5, row 6. How about the columns? It's C1, column 1, column 2, column 3, column 4, column 5, column 6, column 7, column 8, column 9, column 10, column 11, and column 12. So hence we have 12 by 6 linear block code. And once again, if we are given the information polynomial, so x squared plus x, comma x cubed plus 1, and then the generator matrix 1, 0, 0, 1, x plus 1, x, then What is the scalar? Scalar information, and then the scalar code word. Just like we had in the previous case, so we know that scalar information can be given as this 0 to n I sub p x to the power of p, which is I naught x naught plus I1 x1 plus all the way. The power here is 3. Okay, so it's going to be I3 x to the power of 3. Now, I can arrange this again so that I the same as in this case there's no x naught, so that will be 0 dot x naught plus 1 x1, right? Then plus 1 dot x squared plus 0 dot x to the power 3, comma 1 dot x naught plus 0 dot x plus 0 dot x squared plus 1 dot x cubed, right? That's for this part. So now I is the same as 0, 1 for x naught plus 1, comma 0, x1, 1, comma 0 for x squared plus 0, comma 1 for x cubed. So that's 0, 1, 1, 0, 1, 0, 0, 1. So the scalar, so here, scalar information, I will be 1, 0, 0, 1 rather, 1, 0, 1, 0, 0, 1. Then the scalar code word C is the same as I dot G. And then I have to multiply through here, so that would be the same as x squared plus x, sorry, so that x squared plus x, comma, x cubed plus 1 times 1, 0, 0, 1, x plus 1, x. So multiply through, so here, C is the same as this times this, then this times this, so we're going to have x squared plus x times 1, that's it. Then this is 0, comma, then here again, this times this, 0, then this times this, so we have x cubed plus 1, comma, then we now have x squared plus x into brackets x plus 1, right, plus x cubed plus 1 times x. So this is going to give us x squared plus x, comma, x cubed plus 1. Oh, sorry, I'm supposed to close it yet, we're not done, comma, x cubed plus x squared, in of this bracket, plus x to the power 4 plus x, right? And by modulo 2 addition, this will truncate this will truncate this, so this is the same as x squared plus x, comma, x cubed plus 1, comma, x to the power 4 plus x cubed. Now, call that C is the same as summation, p equal to 0 to n, C sub p s to the power of p, which is C naught x naught, plus C1 x1, plus all the way to the highest power here is 4, right? So to C4 s to the power 4. And once we arrange this, so it means that for this, we have C equal so 0 dot x naught plus 1 dot x plus 0 dot no, x squared is there. That's plus 1 dot x squared plus 0 dot x cube plus 0 dot x to the power 4, right? Then comma x to the power of 1 dot x to the power of 0 plus 0 dot x to the power of 1 plus 0 dot x to the power of 2 plus 1 dot x to the power of 3 plus 0 dot x to the power of 4. Now comma 0 dot x to the power of 0 plus 0 dot x to the power of 1 plus 0 dot x to the power of 2 plus 0 dot x, no, that's 1. It's the cube there, plus 1 dot x to the power of cube plus 1 dot x to the power of 4. So we have 0, 1, 0 for x to the power of naught plus this 1, 0, 0, 1, 0, 0, x to the power of 1 plus for x squared 1, 0, 0, 1, 0, 0 for x squared. Then for x cubed we have 0, 0, 1, 0, 0, 1 x cubed plus x to the power of 4, 0, 0, 1 x to the power of 4. So we have 0, 1, 0, 1, 0, 0, 1, 0, 0, 0 x cubed, x cubed, this is 1 and this is 1, sorry for that. So we have 0, we have 1, and we have 0, 1, 1. Then we have 0, 0, 1. So the scalar code word is 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1. That's okay. Now let us look into shift register method. Now, convolution codes are generated by transmitting a data sequence through a shift register. Say we have some shift register arranged this way, S1, S2, S3. So we have the input this way. So we use the convolution codes are usually generated by transmitting a data sequence, okay, through shift registers, which has 2 or more sets, in this case 3 sets of registers or register tabs, filters, with each set transmitting in modulo to other, okay? So they could combine using a modulo to other. Now, each code output, so that this is one possible output, is produced by sampling the output of all the modulo to other once per shift register clock period, okay? So the convolution code derives its name from the fact that the output is obtained by the convolution of the input sequence with the impulse response of the coder. And now, if for instance, we consider an NK convolution code, just like we've been looking at, say a 2 by 1 convolution code, here we know that the rate is the same for this is n and this is k, is the same as 1 over 2. So in other words, we have a rate 1 over 2 convolutional code. Then, if we have a 3-stage encoder having a constraint length of k equal to 3, for instance, then for a 2 by 1 convolution encoder, here we have a constraint k equal to 3. Now the connection diagram looks something like this. So we have 3 shift registers, S1, S2, S3. Now we have S1 connected with S3, S1, S3 are connected by modulo 2 other, and then S1 and S2 are equally connected by modulo 2 other. So we have this going in this direction. So let's say this is a switch. So this is the encoded output. So in this case, we have the input sequence coming in this way, input, and we have the encoded output. Okay. So this is a wraith 1/2 convolution encoder using the shift register method. So here recall that k is given as 1/3, is given as 3, the constraint, and recall that k is the same as m plus 1, such that m, the memory, is the same as k minus 1, which is equal to 3 minus 1, then it's 2. So we have memory to be 2. Note that the error correcting capability is related to the constraint length, which increases with longer lengths of the shift register. Now, this coder produces 2 outputs, say V1, V2. Okay? For every input information using the adders here, which acts as the combinatorial logic. Now, the first output is obtained with the switch in this position. So let's say switch 1, so this is switch 2, while the second output is obtained with the switch in position 2. Now, the first stage of the shift register here holds the input. If, for instance, we feed in the input into this, say a 0, so it means that this first shift register will hold the input, while whatsoever input was holding will be shifted to shift register 2, and whatsoever the shift register 2 was holding onto will be shifted to shift register 3, and whatsoever the shift register 3 was holding onto will be discarded. Okay, so the fact that these other 2 shift registers, or the 2 final stages of the shift registers, are able to hold past inputs, because what was here before is now held by this, and what was here before is now held by this, then they may be regarded as determining the machine's memory. And mind you, here they have 2 memory, because they're able to hold on to 2 past inputs whenever a new input is fed into the first shift register. So if we feed in a 1 here, so whatsoever I say moves here, whatsoever I say moves here. So now, if the input to the half-rate convolution coder is say the input now, let's assume the input, let's say the input here is 11011. That is the input to this encoder. Now you know that each bit in the input sequence will yield 2 outputs, okay? Because once we feed this in with this combination, we get 1 bit. Then with this combination, we'll get 1 bit. So for each bit, we'll have 2 bits as the output. So hence, from this connection diagram, V1 is the same as S1 plus S3, that's modulo 2 addition, while V2 is the same as S1 plus S2. So know that S1 will hold the input, while S2 will shift the input by 1 bit space, and S3 will shift the input by 2-bit space. So if we assume an initial state, let's say the initial state here of the shift registers looks something like this: 0, 0, 0 for S1, S2, S3. Now, when we feed in an input, say 1, okay? So in this first case, we are feeding in an input. We have our input. This is what we have. We want to transmit 1, 1, 0, 1, 1. So 1 at a time. So let's say we feed in an input 1 into this. So in other words, from the initial state, we just feed in an input. Okay. So it means that the first shift register, we hold on to that one input, 1. Then what it held before will be shifted to the second shift register. So here we'll have a 0. And then this 0 will be shifted here. So this will be discarded. Perfect. And then afterwards, we feed in another 1. Okay. Feed in another 1 into the shift register. So once we feed 1, so you realize that this bit will be shifted to the next shift register, and what we have will be shifted to this 0. And then the next bit here, we're taking care of this is a 0. So now we are going to feed a 0 into the shift register. And now once we feed in a 0, this one shift moves to shift register 2, and this one moves to shift register 3. Then we feed in a 1, that's this one. Then once again, 1, then this 0 is shifted to shift register 2, and this one is shifted to shift register 1, and then this one is discarded. Boom. Then we have the last bit, 1. So once we feed that in again, 1. So what do we get? Get a 1 here, then this one is shifted to this, and then the 0 is shifted to that, and then that is discarded. Okay? So in summary, you see that where we have the input as 1, 1, 0, 1, 1, then now we have the shift register S1, S2, S3. So here we say that the shift register 1 holds onto this input 1, 1, 0. One, 1, 0, 1, 1. And then the shift register 2 shift by 1 bit space. So 0, that's 1, 1, 0, 1. So this is discarded, right? So the shift register 3 shift by 2 bit space, 0, 0, and that's 1, 1, 0, 1, 1. So all of these are discarded by shift register 1 and 2. Now the output V1, V2 follows directly. Now considering 1, 2, 3, 4, 5 bits. So x1 plus s3, that will be 1. x1 plus s3, that's 1. That's 1. s1 plus s3, 1 plus 1 will be 0. Then this is 1. And the same thing goes for this. 1, 2, that's 1. That's 0. That's 1. That's 1. That's 0. Okay. So hence, for the input sequence for which we had 1, 1, 0, 1, 1. So the output bits are 1, 1, 1, 0, 1 for this is 1, 0. and for 0 is 1, 1, and for this one is 0, 1, and for this one is 1, 0. Perfect. So now let us consider the state diagram method. State diagram method. Now, generally, we have an end for an end stage register. For an end stage register, we have 2 to the power of n minus 1 states. So in our design, where we have the state diagram, say S1, S2, S3, for which we have the input, okay? And then we have 2 outputs, output 1, output 2, as designed, okay? So you realize that we have 3 registers here, okay? So for 3 registers, it means n is equal to 3. So technically, we have 2 to the power of n minus 1, which is 2 to the power of 3 minus 1. That's 2 to the power of 2, which is 4 states. We have 4 states in this case. Now, if we have 4 states in this case, to generate the state diagram from the given connection, that is here, we have this and this joined together. That gives us this first. Then this and this joined together to give us a second output. So for us to use this connection diagram, for which this is V1, this is V2, we must first design the state table. But note that we have 4 states. So let's assume the 4 states are designated as A, B, C, D. Okay? And each state can emit 2 bits. Okay? 0, 1, 0, 1. Each state can emit 2 bits. 0, 1. Each state can emit 2 bits. 0, 1. Now, hence, each state has 2 possible outcomes. So that if each state have 2 possible outcomes, then we have 2 times 4, which is 8 total possible outcomes. Okay? Like in the previous example, for an all 0 initial state, that is, we consider the shift registers to be in an initial state of all zeros, then we can design the state table. So if we have initial state, for instance, so we have something like this. Then let's assume we have the state and then the state transition. To follow the line here. Okay. Then we have our shift registers now. S1, S2, S3. So here, 2, 3, 4, 5, 6, 7, 8. So something like this. afterwards, we're going to have the output to be 12, right? Pardon the irregular lines. Okay, so this is V1, this is V2. Now, from here, we know each state can take on two possible outcomes. It's either it emits a 0 or a 1, okay? So for A, it can either emit a 0 or a 1, okay? So it can connect with A, it can connect with B. Now for B, it can connect with state C or state D, okay? It can emit a 0 here or a 1, a 0 here or a 1 here. Now for C, it can also connect to either state A or state B, can emit a 0 or a 1. And for state D, can either connect with state C or state D, and it can emit either a 0 or a 1. Now, recall that the initial state here of the register is all zeros, right? Now, if we feed it with a 0, okay, so it means S1 will hold on to the new input 0, and the initial input will move to this, and this will move to this, so that will be 0, 0. Okay, now what if it's a 1? Okay, now for the initial state, we feed it with a 1, so we have 1 here. So with a 1 in this, then this initial state register holds onto the 1 bit, then the initial 0 moves, and that also moves. Now, in state B, we have 1, 0, 0. So from state B, the initial state is now 1, 0, 0. Okay, so when we feed in a 0 here, so the S1 will hold on to the 0, and that will shift, so that will be 1, 0. And when we feed in a 1 here, so S1 holds on to 1, and the 1 shifts to register 2, 1, 0. Okay, and now in C, the initial state is now a 0, 1, 0, right? 0, 1, 0. So when we feed in a 0, so this 0 moves to the next shift register, that's 0, and the 1 moves to the next shift register, that is 1. And when we feed in a 1 here, so this 0 moves to the next shift register, and the 1 moves to the next shift register, 1. And now, for state D, the initial state now becomes 1, 1, 0. This is the 1, 1, 0, 1, 1, 0. And we'll feed in a 0, so that'll be 0, and this one will shift here, and this one will shift here, 1, 1. And when we feed in a 1 here, the 1 will shift here, this one will shift here. So we have that. And once again, recall that V1 is x1 plus x3 S3, V2 is S1 plus S2. So once we do that, x1 plus S3, 0, this plus this is 1, this plus this is 0, this plus this is 1, this plus this is 1, this plus this is 0, and this plus this is 1, this plus this is 0. Then this plus this is 0, 1 plus 0, 1 plus 0, 1, 1 plus 1, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 1, 1 plus 1, 0. So we have 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. So with this, we can design the state diagram. So hence, the state diagram, this is a state table. And then we now design the state diagram. So we have state A here, then we have state B here, we have state C here, and then we have state D here. Okay, so when A moves to state A, the output is all zeros. So it means this moves from this to this, and mind you, it emits a 0, so you can put up a 0 here. So the output is 0, 0. Right? And then when A moves to B, it emits 1. So B, this, so let's assume it emits a 1. And then the output is 1, 1, 1, by this state table following the connection diagram. It's a connection diagram. So the point is, all of these codes will vary depending on the connection diagram. And these code words will also vary depending on the connection diagram. And the outcome of the state table will also vary, as the output will also vary depending on this connection diagram. Okay, so state B can connect to state C, okay, by emitting a 0 when it emits a 0. So sorry. So from B to C, so we have B to C when it emits a 0. So let's put a 0 in here, and the output is 0, 1, 0, 1. And from B to D, it emits a 1. B to D when it emits a 1, and the output is 1, 0, 1, 0. Also, from C to A, it emits a 0, and the output is 1, 0. And from C to B, from C to B, we have, when it emits a 1, then the output is 0, 1. And also from D to C, when it emits a 0, and then the output is 1, 1. And also from D to D, when it emits a 1, then the output is 0, 0. So let us use it to decode our previous input. We call the input sequence. We have input sequence. Okay, before we go on, so what was the decoded system? Previous one. So we had, let's just put it somewhere to be sure if we're correct. 1, 1, 1, 0, 1, 1, 0, 1, and 0. 4, 1, 1, 0, 1, 1. Okay, this is what was decoded, right? So let us go on. So in our case, we have the input sequence 1, 1, 0, 1, 1. So now the output sequence, or the decoded sequence, let's say the decoded sequence in this case, decoded sequence. Now, when 1 is transmitted, now coming from state A, now if it were to be a 0, then we'll move this way, but now it is a 1, so we have to move this way. So it means from state A, we are moving this way, right? Because 1 is emitted. And what we have here, the code word is 1, 1. And afterwards, from state B, we have to move again based on the fact that 1 is emitted. So we have to come this direction. Then we get to D, and another 1, 0 is emitted. Now from D, a 0 is emitted. So if a 0 is emitted, we go this part, and then that is 1, 1. Then from state C, a 1 is emitted. So when a 1 is emitted, this is a 1, part for 1 is emitted. So we'll come this route. So that's a 0, 1. And from State B, another 1 is emitted. So we have to come this route again the second time, and that is 1, 0. Now, if you compare with what we got using the register method, we got a 1, 1, 1, 0, that's 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, then 1, 0, 1, 0. So meaning with the register method, we were able to achieve the same result with the state method, and that's what it is. So now we'll consider the tree method. Tree diagram method. So another way of showing the states of the encoder is by using the tree diagram. And this diagram is for the encoder taking in 1 bit k at a time, okay? And here we have that. Let's assume the data input gets in here, then we have the shift register with the initial state of all zeros for S1, S2, S3. Then you can see that you can move this way, just drawing something very rough, okay? Move this way, where this is state A, this is the uppermost branch, this is the lowermost branch. Then I'm getting here. So in this case, the 0 is emitted, and in this case, a 1 is emitted. So because each state can emit either 0 or 1. So when 0 is emitted here, so it's all 0, so they will shift by the same amount. Now when 1, then when the shift register goes onto 1, then 0 shifts from the S1, 0 shifts to S2, then the same thing. Now come to this point. Here we have another set of shift registers here, another shift registers here. Then here we have another set of shift registers here, another set of shift registers here. So at this point, branches to A of the, recall that we have state A can move to AB, state B can move to CD, state C can move to AB, and state D can move to CD, right? So now this state A to B. So state A can connect with A, B, and now recall the branch again. So here the initial state is all 0. So when it is 0 is emitted here, 1 is emitted here, so it goes on to 0, then the others are shifted. Here it goes on to 1, then the others are shifted. Now in this case, 1, 0, 0 is the initial state, 0 is emitted here, 1 is emitted here. So when a 0 is emitted here, then this 1 is shifted, and then the 0. So when a 1 is transmitted here, then the 1 is shifted, and the 0. So this is how we go on and on, okay? And here again, have 2 registers here, then we have 2 registers here, and once again we have 3 registers here, then we have 3 registers here, and same applies here, 3 registers here, then we have 3 registers here, then we have 2 registers here, then we have 2 registers here. So once again, this is point A, this is point B, right? So almost, and this is now point C, this is point D, because B can connect to CD, right? CD. So at this point now, the initial state is 0. So we have a 0 here, a 1 here, 2 possible outcomes. So you can emit a 0 here, you can emit a 1 here, you can emit a 0 here, and you can emit a 1 here. So when it emits a 0, it's all 0, 0, 0. When it emits a 1 here, that's 1, 0, 0. So there's 1, 0, 0. So when it emits 0, then the 1 shifts and 0. So when it emits a 1 here, so this one shifts to this, and the 0 shifts accordingly. Same here, so the 0, 1, 0 as the initial state. So when we have a 0, so the 0 shifts and the 1 shifts accordingly. So same here, 1, 0 shifts, then that 1 shifts 1. Then the same case here, when we have a 0 here, and the 1 shifts, and then the 1 shifts. So we have a 1 here, so that shifts, that shifts. So we can go on and on in terms of populating this, so that the upward arrows on the branches indicate the change in the shift register, okay, that incoming 0 or 1, just like as I mentioned. Okay, perfect. So in this case, you observe that state A, for instance, in state A, now the branches lead to the shift register storing either 0, 0, 0 or a 1, 0, 0. And for state B, the branch for state B can either store a 0, 1, 0 or a 1, 1, 0. Right? Now for state C, the branch can either store a 0, 0, 1 or a 1, 0, 1. And for state D, the branch can store either a 0, 1, 1 or a 1, 1. Okay? So in other words, the encoder can be in one of 4 different states as either A, B, C, or D on the tree diagram, and the states repeat. Okay. So let us talk about the final technique, the Trellis diagram method. Okay. So another way the convolution encoder may be designed is by using the Trellis diagram, just like the case of the 3 diagrams. We have 3-stage encoder. There isn't the same encoder. So in other words, for a 3-stage encoder, that is where the stage here is referred to as the registers, the number of registers. So we have 2 to the power minus 1, which is 2 to the power 3 minus 1, that's 2 to the power 2, that's 4 states, okay? So we have 4 possible states. So now, we say that we have state A, B, C, and D, and we know state A can lead to A and B, state B can lead to C, D, state C can lead to A, B, and state D can lead to C, D. Perfect. So in the Trellis diagram, we use dots, okay, to represent each state. Okay, we use dot to represent each state. And the 2 branches emanating from each dot, that is the uppermost and the lowermost branches, represent the change that occurs when either a 0 or 1 is, enters into the shift register, respectively. So now, I want to design the state diagram. So in this case, we know we have state. So we have either A, B, C, D, right? So we say we use dots to represent the state and the states. So dots, okay. Some of these dots repeating. What's that? Depending on the length of the sequence we wish to decode. So could continue to repeat this on and over and over. So let's write this. Okay, these are the possible states. Okay, now let's use a different color. we already know that A can take on two states, AB, then B from CD, then C to AB, and D to CD, right? So it means that we can move from state A to state A, or state A to state B. Okay, now recall that we already have our state diagram, which we don't want to repeat again, so we just pull it up because we already derived that from previous method. So we have S1, so let's change the color. We have S1, S2, S3, then we have V1, V2, right? So we have 0, 1, 0, 1, 0, 1, 0, 1. So these are each states. Okay, so then already so have 0, 0 here based on previous design. 0, 0, 0, 0, 0, 0. And you want to review or revise the previous lecture, the previous methods to understand how we derive this. So let's just move quickly. This is 0, 0, 1, 1, and this is 0, 1. This is 1, 0. Using V1 is the same as S1 plus S3, and V2 is the same as S1 plus S2, right? By using the connection diagram. And then we have this to be 0, 0, 1, 1, 0, 0. Okay. So meaning from state A, means that to state A can either move either AB, from state B can either move C, D, from state C can either move A, B, and from D we can either move C, D. Right? Now, when we move from state A to state A, the output is 0, 0. And when we move from A to B, the output is 1, 1. Okay, so we can populate this. 0, 0, 0, 0. And then from state B, we can move to state C. From state B, we can move to state C. And then the output is 0, 1. And from B, we can also move to state D. And that is 1, 0, okay? So we can move to C, and we can move to D. Okay, so we populate that. Okay. Now from C, we can move to A. So from this state, so we can move from this state to this state. Or that these are all states, right? These are all states. These are all states. These are all states. So now we can move from C to A. That's this, C to A. Then the output is 1, 0. And then from C to B, the output is 0. So once again, from C to A, this is 1, 0. C to B, this is 0. So then finally, can move from D to C, B, from D, this state to another state, D to C, that is 1, 1. Then D to D, this is 1, 1. Then the output is 0, 0. So from D to E, D to C, that's 1, 1. Then D to D, 0, 0. And from D to C, 1, 1. From D to D, 0. Recall that we have the transmitted code word, the transmitted sequence. For instance, the transmitted sequence, as we have previously, 1, 1, 0, 1, 1. So now, recall that the uppermost branch is a 0, because emitting a 0, and the lowermost branch is a 1. So when we emit a 1, so it means this is going to come this way. So let's use a red. We'll move from state A to state B, tracing this part to state B, and the output is 1, 1, because a 1 was emitted. Now, from state B, we can either move to state C or D. And now we have another 1 emitted. So when a 1 is emitted, if a 0 was emitted, we go to state C, but now a 1 is emitted, so we're going to go to state D. So we're going to trace down. So, and the output there is 1, 0. And from state D, a 0 is emitted. So the uppermost branch is a 0 and the lowermost branch is a 1. So if we have to, since it's emitting a 0, so from D we are going to C. So that's a 1, 1. Right? Then from C, it emits a 1. So it's either we'll go to A, that's emitting a 0, or we'll go to B, which is emitting a 1. So we'll go to B. And in going to B, the output is 0, 1, right? 0, 1. And then from B, it emits a 1. So it's either from B now, it's either we'll go to C or we go to D. If it's a 0, then we are going to C. Now if it's a 1, we are going to D. So, and it's a 1, so we are coming back. Okay, so let's use this. So it means I'm moving from here to here. Perfect. Good. Then observe that is the 1. And just like always, in our previous system, where we use the register method, where we use the state diagram method, we achieved the same outcome where what was decoded was a 1 1 1 0, a 1 1 0 1 1 1. That's fine. Now, what if one of these bits is in error? Okay, so let's assume one of the bits have been received in error. And now we have to play around correcting that. Okay, so let's assume this was received in error. Okay, so that rather than receive a 1 1 there, let's assume we received 1 1 1 0 1 1. Then probably here we now receive the 1 0. Then we received say 1, right? Okay, so this is a 1 0, so it's a 1. It's not a 1. This is a 1 0. Sure. It's a 1 0. Because here it's 1 0. What? It is a 1 0. Because from this point to this point, the output emits a 1 0. It's a 1 0 from D to D, right? It's a 1 0, not a 1. And the previous is also a 1 0. So let's assume we have one bit in error. So okay. Let's even say 2 bits in error. Okay, 2 bits in error. So it means this and this have been received in the 2 code words in error. Now, this algorithm is going to trace that's 1 1 1 0. Oh, this and this are now in error. Okay, so yeah, then this is the third. Yeah, we are good here. Now 1 0 could take on this part. Such that it now emits a 1 that's going back to A from C to A. Yeah, that's 1 0. Then it comes here. That's a 1 1. Okay. Then alternatively, from this part, go through this part. That's a 1. That's from a C to B. That's a 0 1. And then choose this possibility. That's 0 1. That's 0 0 1. Then it can equally choose this possibility. That is taking on 1 0 0 0. Right? And then we can equally take on this possibility. For which we now have 1 0 for which we have 0 1 1 0, right? 0 1 1 0, for which all other bits are equivalent. Okay, so in this case you will observe that in this case, this and this are in error. They have two conflicts here because we're supposed to receive a 0, 1, 1, 0, so we're receiving 1, 1, 0, 0. Then in this part also, from here to here, we are receiving a 1, 1, 1, 1. This is also two conflicts. Then here we are receiving 0, 1. That's from C to B. 0, 1, 0, 1. So we are receiving one conflict here. Then in this case, we have a 1, 0. Here we have 0, 1, 1, 0. Okay, which actually tallies. Okay, and in this case, this tallies with what was transmitted. So technically, you see that all of the conflicts are not equally likely. Such that the decoder we now have to choose the most likely part, okay, because it has idea or information about what was transmitted, okay, because this scheme is running on the transmitter, okay, and as such is able to decode which of them is in error, and hence this is favored, which is equivalent to this. And for that reason, the Trellis diagram or Trellis decoding scheme is usually referred to as the maximum likelihood decoding scheme. Okay. Now we have just one more thing to deal with here. Now, what if so far we have been able to deal with 8 possible code words in the previous example. Okay, what if we have about 16 code words in the code book? Now, how will the Trellis diagram be designed should we have this possibility, 16 code words in the code book with 3 possible outputs? And now, let us use a different connection diagram. Now, should we have this connection diagram? There's a connection diagram. Here we have 3 shift registers, and as such, the number of states is the same as 2 to the power of n minus 1, where n is 3, n is equal to 3, so that's 2 to the power of 3 minus 1. So that will give us 2 to the power of 2, that's 4 states. We have 4 possible states. But now we are considering 16 possible code words, right? So the number of code words per state will therefore be 16 divided by 4, which is equal to 4 code words per state. Hence, should we have the truth table? Let's take the first 4 bits, that's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1. So it means that these 4 sets will be in the same state, okay? for code words in the same state. Then another branch of 4, that will be another branch of 4, another branch of 4, another branch of 4. So that will be state 1. Then the next branch of 4 So the other group of 4 being state 2, then the third group of 4 state 3, and the third group of 4 state 4, right? So hence, state transition will be in the interval 4. So state transition will be in the interval of 4. And for code words, we emit a 0, 1, 0, 1, okay? At a given instant of time. So in a state, for code words, we emit a 0, 1, 0, 1. And then, if we now consider a P step Trellis diagram, so that P is the same as 0, 1 all the way, then if, for instance, P is equal to 7, okay, then we can construct the state table. We can construct the state table of the 7-step Trellis diagram that will be able to detect and correct some possible code words. So in this case, output bit 1 is the sum, that's output bit 1, is the same as the shift register 1 plus 2 S1 plus S2. The output bit 2, this is the same as S2 plus S3. Then output bit 4, bit 3, output bit 3 is the same as S1 plus S3. So with this, we should be able to get things going. Okay, so now let us design the code word. So let's assume we want to use a 7-step Trellis diagram to decode certain code word. But before we do that, let us design the state table. So the state table. Now we have the initial state A. Okay. Let's use let's populate this table. Okay. Okay. So now we have this, but recall that we have 16 code words, right? Possible code words. And we already said code word per state. We have 3 registers, so it's 2 to the power of 3 minus 1, which is 4 states. So we have 4 code words per state. So we're able to have 4 states. And now it's a 7-step Trellis diagram. Okay. So since it's 7-step, we already said for P step, can take P equal to 0, 1, 2 all the way, and now we have to 7. And then it means that for each 4 code words that are in the same state, like we mentioned earlier, like we showed in an earlier slide. So we have 0, 1, 0, 1. So it means that two of these will either be a 0 or two of these will either be a 1. So we can choose state A now from state 0. So it means that two bits or two code words will definitely be in the same state. They will either emit a 0, two code words will emit a 0, while two code words will emit a 1, right? Okay, so if we say from P equal to 0 to 7, then 2 could be in that same step, step 0, step 1, step 2, step 3, step 4, step 5, step 6, this step 7, right? Good. Now, each state, we can move each state by 4 code words per state. So in other words, we have 4 states, and the interval here happens to be 4, such that we can move from the 0 to 4. And for these 4 code words, remember, they are all in the same state, so we can either move from the 0 to 4. And then the next interval be from state 1 to 5, which is 4 steps, okay, 4 code words. 1 to 5, then 2 to 6, 2 to 6, 3 to 7, 3 to 7. So that the difference, 7 minus 3, is 4. Okay? So that we have 4 code words per state. Now, so if we have the shift registers, we have shift register 1, shift register 2, shift register 3, okay? And shift and the input. So if we have the input, which must be a 0 or a 1, 0, 1. So 0, 1. So 0, 1. Could either be a 0 or a 1. So from this step, we can either emit a 0 or 1. In this step, step 2, we can either emit a 0 or 1. In step 3, we can emit a 0 or 1. In step 2, in step 3, a 0 or 1. In step 4, we can emit a 0 or 1. In step 5, we can emit a 0 or 1. In step 6, we can emit a 0 or 1. In step 7, we can emit a 0 or 1. Okay? Good. And based on our shift register notation, we can populate this using the truth table. So let's just do that. So if this is the initial state of the shift register, and now should we feed the shift register 1 with the input, then we'll have shift register 2, shift register 3. So it means that the shift register 1 will hold onto this input as 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0. Then the original parameter stored in shift register 1 will be shifted to shift register 2, which is all this, that's 0, 0, 0, 0, 0, 0, 0, 0, and the parameters held by shift register 2 will now be shifted to shift register 3. 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now, you'll recall that we have the output bit 1, output bit 2, and output bit 3. Now, the output bit 1 is the same as shift register 1 plus shift register 2 then output be 2 is the same as shift register 2 plus shift register 3, while output be 3 is the same as shift register 1 plus shift register 3. So once we begin to play with these are this lead to our new state. This then 0 or 0, 1, 2, 0. Then we have 1, 0. Now 1, we have 0, we have 1, we have 0. We have 1 here, we have 0. That's this plus this. This plus this is 0. This plus this is 1. This plus this 0. Plus this 1. This plus this is 0. This plus this 1. And this plus this 0. So S2 plus S3 modulo 2 addition. So we have 0, 0, 0, 0. Then 1. Okay. That's S2. S3, S2 plus S3 is 0, 0, 0, 0. Once again, S1, S3, S1 plus S3. So we have 0, 1, 0, 1, 0, 0, 0, 1. Then still we have 0, 1, 0, 0. So with this, we can design the Trellis diagram that will be used to decode any given code word. So let us recall that the dots happen to be the state, and here we have 7 steps. So I'll pause the video while we populate the table. Okay, so now we have the 7 steps from 0 to 7, and then we have the states. And from this, we can move from 0 to 0, which is either from this to this, and the output bit is 0, 0, 0, 0, 0, 0. Or we can actually move from 0 to 4. 4 steps, that's 0 to 4. So we can move to, we can move all the way. Then that will be all 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's from 0 to 0. The output is all zeros. Now from 0, step 0 to step 4, we have 1, 0, 1. Here we have 1, 0, 1. So we can populate that all the way. And then the next step is to move from 1 to 0. Now we can move from 1 to 0, from 1 to 0, 1 to 0, to 0. And then we can also move from 1 to 4. To 4. Right? 1 to 4. And we know their outputs, so we just populate that once again. So the next step now is to move from 2 to 1, from 2 to 1, 2 to 1, and from 2 to 5. from 2 to 5, after 2 to 5. So 2 to 1, 2 to step 5. We're going to populate that once again. Once again, we move from 3 to 1, from 3 to 1, and from 3 to 5. 5, right? 3 to 5. So from 3 to 1, 3 to 5. 3 to 1, 3 to 5. Can now move on to 4 to 2 and 4 to 6. So from here, 4 to 2 and 4 to 6. Move from this state to 4 to 2, then we move 4 to 6. And also we have 5 to 2, 5 to 6. So that will be 5 to 2, 5 to 6. So we have 5 to 2, 5 to 6. Can now move from 6 to 3 and 6 to 7. So from 6, I move to 3, then I move to 7. From 6 to 3, then I move to 7. Now, once again, I want to move from 6 to 3, 6 to 7, 6, 6 to 3, 6 to 7. So from 6, I move to 3, then from 6, I move to 7. From 6, to 3, then from 6, I move to 7. And then the bit place, that's 6 to 3 is 1, 0, 1. So this is 1, 0, 1. This is 1, 0, 1. So 3 times 6 to 7 is 0, 0, 0. So this is 0, 0, 0, 0, 0, 0. So populate the others. So finally, the Trellis diagram, the 7-step Trellis diagram. So we'll have to go from step 7 to step 3. Step 7, step 3, step 7, step 7. So step 7 to step 3, then step 7 to step 7. Then we have 1, 0, 1 for this and 0, 0, 0. 0, 0, 0, 0, 0, 0, 1, 0, 1. Between step 7 to step 3, 0, 1, 0, 0, 0. So this is the 7-step Trellis diagram for the connection diagram and the state table. So when the connection diagram varies, then these output bits will also vary. Okay, the output bits that will be used for decoding will also vary. So now we want to decode something. So let us wipe this part of the board. Let us assume we have the received sequence Let's change this to black. So we have the received sequence. One 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 0 1 1 1 0 4 6. Then I want to figure out the decoded sequence. Say decoded sequence. I also want to tell the path weight. Okay. Now, in order to evaluate the path weight, the received code word is compared with the decoded code words. These are the decoded code words, right? These are the decoded code words. So we have to compare this received sequence with the decoded code word. And then by so doing, the path weight is the same as the uppermost weight divided by the lowermost weight. And then for us to do this, so let's assume taking the 1 1 1 for instance. So we are moving from here. For us to move this way, so we have two options: either we'll go upward or we'll go downward. And now the path weight will be the same as comparing 1 1 1 with 0 0 0 0 0 0. That's the uppermost. And then the difference here is 1 1 1. So here we have 3. Then for the lowermost, we have the received sequence and the decoded 1 0 1. And the difference now is 0 1 0. So that's over 1. So here the weight is 3 over 1. So we're going to go down. Okay. So we're going to go down. And then the decoded code word there is 1 0 1. That's 1 0 1. So is it here? 0. And in the case of the 0 1 1, so the weight now be 0 1 1 received compared with the decoded 1 1 0, and then we have 0 1 1. That's from step 4 with 0. Right? So this will give us the weight of 1 0 1, that is 2 over 0 0 0 over 0. So again, we have 2 over 0 weight here. So it means we are going downward because the path with the least weight is downward here. So actually diagram goes downward. Okay. Then the decoded code word there is correct. So that will be 0 1 1. The same vein, when we compare the weight at this point, that's step 5. So at step 5, we can either move to step 2 or step 6, right? From 5. Oh, we're in step 6 here, okay? And step 6. So from step 6, we can either move to step 3 or step 7, okay? Now the weight we received 1 1 1. So the uppermost is 1 0 1. It's 1 0 1. Then the weight here is 0 1 0. So we have 1 over, then the lowermost weight, that's 1 1 1. Then with the difference from this part, it is going to 0 0 0, right? This part is 0 0, lowermost part is 0 0 0. So that's 111, which is 3. The weight is 3, or 3. So here is 1 over 3. So the uppermost part have the least weight. So we're tracing upward. Tracing upward, right? Down to step 3, right? And now the code here will be 101. 101, okay? Which is the coded 101. Once again, we have received 110. Here we have 110, right? So from step 3, we can either move to step 1, or we move to step 5. And to step 1, the weight is 011, 011, 011. And here the weight is 101, that is 2 over. Now, if we are tracing downward to step 5, the decoded code word there is 110, right? It's 110. This is 110. So once we take the weight is 0, so it is 2 over 0. So the lowermost part have the least weight, so it's going to trace downward. Okay. It's going to trace down. Trace down. Yeah. Then the decoded code word here is 10. And then we can go on and on in this scheme to decode and correct code words. And here we can see that this code word was received in error. This is the this is the correct code word. But this was received correctly, and this also was in error. So you can see that this has the capacity, that the training diagram has the capacity, or better say have the capacity to both detect and correct errors. Okay, and this is usually referred to as the Viterbi maximum likelihood decoding scheme. Likely because the receiver chooses the a posteriori most likely message. In summary, convolution codes are mostly used in correcting burst errors, okay? Not just single bits. And the goal of the decoder is to determine the most likely input stream of the encoder, given a knowledge of the encoder characteristics and the received bit stream, and the minimum distance between the received sequence and the points representing all possible sequences which could have been produced by the coder in a multi-dimensional space is usually chosen as the correct sequence in the decoding scheme. I think this is a good place to stop. Hope to engage us in our next lecture. Bye for now.